Next, we will discuss the convergence of sequences that are defined recursively. And as we previously discussed, the sequence that are defined by a general formula can be easily converted into continuous function, and the limit of that continuous function can be analyzed. However, that's not enough for, that's not sufficient at all for functions defined recursively, because to define a function recursively means we don't have an explicit formula for the nth term, so it's not so easy to convert or relate a given sequence to some continuous function. So essentially, we're going to learn a theorem that is called it's a very short theorem. It only has like 5 words. But in order for us to learn this theorem, we have to understand, introduce and understand the following terms. We have to understand what a monotone sequence is. We have to understand what a bounded sequence is. And as soon as we do understand these 2 terms, we'll be able to make this theorem and use it to investigate the convergence of a sequence that is defined recursively. So this is our goal, and let's get started. So we say a sequence is increasing if every consecutive term is greater than its every successor is greater than its predecessor. Let's put it that way. So symbolically we can write it like this. We also say similarly that a sequence is decreasing if the successor is less than its predecessor. So less than or equal to. So these are the definitions. And we have this, an umbrella term, a sequence. We say sequence is monotone. So monotone is an umbrella term if it is increasing or decreasing. All right, and let's do an example. So the first example, we just have to show that the following sequence is decreasing. And we're going to have actually 2 different methods. So first we're going to do method 1, and I call it the algebra way. And in this algebra approach, we have to establish the following. We have to establish that the successor is less than its predecessor for all natural numbers n. And we're going to do that by kind of solving this inequality, but in the formula where we have n plus 1, the index, we're going to replace n with n plus 1. So basically we have to show that this inequality holds for all natural values n. And let's multiply both sides by n plus 1, n plus 2. So we get this. And again, where did n plus 2 came from? Well, that's what this is equal to. So now we're just multiplying the both sides by the common denominator. And we can reduce the 2's, subtract the n's, and we get a trivial identity here, which means that this inequality is always true. So this, again, none of the particular lines is the proof. It's this whole argument is what we consider the proof that this sequence is decreasing. Now let's do the same task, but the calculus way. So by calculus way, I mean we're going to consider a function f of x on which this sequence resides, and we're going to restrict the domain to only positive values, not only positive, but to values of x greater than or equal to 1. And recall that a function is decreasing, and remember, if this function is decreasing, then sequence also must be decreasing because it leaves on this function. And f of x is decreasing only when, not only, but we can identify when it is decreasing when derivative of this function is less than 0. So in the calculus way, we're going to find the derivative of this function using our calculus skills, and then we're going to convince ourselves somehow that that derivative is less than 0. And if it is less than 0, which it is indeed in this case less than 0, because x plus 1 squared is always greater than 0, and when you take positive number, divide by positive number, and throw the negative in the front, of course you're going to get something that is negative. So again, none of these particular lines is the proof, it's the whole argument that we consider the proof. Alright, let's do another example. Similarly, let's convince ourselves that this sequence is increasing. And let's do it first using the algebra way. So in algebra way, we have to make sure that the successor is greater than its predecessor. So we're going to throw n plus 1 into this formula to figure out the left-hand side of this inequality. And again, similarly to how we did it before, this is what we want to show. And we're going to multiply both sides by the common denominator. So we're going to have n plus 1 times n here. Distributing everything. And we have 0 is greater than negative 2. So it's not always this simple, but it is always possible to show that this inequality holds for natural values n. So again, this is a convincing argument. Let's do the same task using the calculus approach. And what are we going to do here? We're going to create a function f of x, and we're going to find its derivative. And here we're going to use the quotient rule. Derivative of the numerator times the denominator minus derivative of the denominator times the numerator, and we have 2 over x plus 1 squared. This is always positive. Why? Because we have something positive divided by something positive. Of course, it's going to be positive. So since the derivative is positive, that implies that the function is increasing. So we provided a convincing argument that this sequence is an increasing sequence. Let's do another example. This time let's take something less nice. And the question is it monotonic? Now, or monotone, I guess. In order for it to be monotone or monotonic, I forgot which word I used here. Monotone, I guess. But monotonic is another word. the answer is it would be yes if it was strictly increasing or strictly decreasing. So we would say no if it's not increasing, decreasing, or that is if it's changes its behavior. So first it's increasing, then it's decreasing. So in this case, we can investigate this sequence, and first we would maybe try to write some of the terms. The first term will be 4, the second term will be 6, and you can see how it's just going to be bouncing between 4 and 6. So when you see such behavior, then the answer is no, it's not monotone or monotonic. Alright, so let's move on to the new set of definitions. And a new definition is, we say a sequence is bounded above if there is a number, so some large number, may not be large, but some number such that it is greater than any element of a sequence. So if that's true, then the sequence is said to be bounded above. Now we say that a sequence is bounded below if there is some number m, small or may not be small, such that every element of the sequence is greater than that number. And we say a sequence is just bounded, so without specifying above or below, just bounded, or bounded means above and below, because by definition we say it's bounded if it is bounded above and below. So let's discuss whether this sequence is bounded above, and the answer is yes. And it takes a little bit more effort to figure out what the bound is, but here we can speculate and assume that the bound is 1. And to show that it's bounded by 1, we want to show that this inequality holds for all values of n. And since n is positive, we can multiply both sides by n plus 1 and establish the following trivial identity, meaning that it's always true. Meaning that the above inequality is also always true, which means that it's bounded by 1. So now let's investigate whether this sequence is bounded below. The answer is also yes, and we can easily establish one bound. There could be many bounds, right? But one bound would be m equals 0. How so? Because if you look at all these elements, they are actually, the first element will be 0, the second element would be 1/3, then it will be 2/4, 3/5, and so on. So it's clearly bounded below because n minus 1 and n plus 1 are always greater than or equal to 0. Now let's investigate whether n squared is bounded above? The answer is no. And why is that? Because if you try to visualize this sequence, you're going to see it is 1 at 1, 4 at 2, and so on. It resides on this y equals x squared graph, which doesn't have an upper bound. So for any n, there is for any m, for any number m that you can think of, there is n such that n squared is greater than m. So this is the reason why there is no upper bound. However, is it bounded below? The answer is yes. How so? Because n squared is always greater than or equal to 0, so it is bounded below by at least this value, 0. Let's do another example. How about this sequence? Is this sequence bounded? Well, sine function, regardless of what the input is, so you can literally put anything inside, is always bounded by 1 and -1. So the answer is yes, this sequence is bounded because it is bounded above by m equals 1, and it's bounded below by m equals -1. And let's also, I want to look at one of these previous examples, 2 over n plus 1. Let's see if 2 over n plus 1 is bounded. Let's see. So one way to investigate the 2 over n plus 1 is to plug in a few values. So when n equals 1, we get 1. When n equals 2, we get 2/3, 2/4, 2/5, 2/6, etc. So what do we see? We see that it's getting smaller and smaller. Actually, as a matter of fact, earlier we convinced ourselves that this is a decreasing sequence, and if it is a decreasing sequence, it is bounded above by its first term. So it is bounded above by m. Now, is it bounded below? It actually is bounded below. Why? Because since n is positive, we have two positive numbers, the ratio of two positive numbers, so of course it has to be positive. So this sequence is actually bounded below by 0. So the answer to the question, is this bounded? The answer is yes, because it is bounded above and below. All right, now that we established this vocabulary, now we can go back to this to revisit our goal. And the goal was to, I guess, provide this theorem, which I said only has 5 words. So the following theorem is the only tool we're going to have that will allow us to analyze recursive sequences in general. And it states the following: a bounded monotone sequence converges. That's it. Just this 5, I guess, depending on how you count, or 4 words. And let's see what it says. Basically, it says a bounded monotone sequence converges. So if you can prove that your sequence is bounded meaning it doesn't go above certain value m and doesn't drop below certain value lowercase m. And at the same time, it is monotone, meaning it's either always increasing or always decreasing. Then the theorem says it has no choice but to converge. And another way to look at this is if you look at a monotone sequence, let's take a look at the increasing one. There are really only two choices there. A monotone sequence keeps increasing, increasing, increasing. So the two choices that it has is either it's going to kind of settle down here and converge to some value L, or alternatively, it's going to break through every limit you set and go to infinity. And basically by saying that your sequence is bounded, you eliminating this possibility. So any monotone sequence that is bounded must have a limit. So this is like a easy visualization of this fact. We're not going to prove this theorem, but we are going to use it. So a couple easy applications or examples of this theorem will be from the same examples that we already did. Earlier, we convinced ourselves that this sequence is decreasing and bounded. And by this theorem, it converges. Notice how the theorem doesn't tell us what it converges to. It only tells us that the sequence converges. So to figure out the limit, we may have to do, I guess, some extra work. And let's not do this work for this sequence, because we really don't need this theorem here, but so let's not be concerned about the limit at this point. All right. Also, earlier we developed that this sequence is increasing and also is bounded. Therefore, this sequence also converges. But again, that's not the reason why we have this theorem. So this theorem basically becomes the only tool that we have to analyze the sequences that are defined recursively. So let's consider the following problem. So a sequence is defined recursively like this, and the term is 2. And the question is, analyze the convergence of this, investigate the convergence of this sequence. And we cannot use the we cannot turn this sequence into a continuous function because there is no general formula. So the only tool we have is the that short 5-word theorem. Now, before we start applying the theorem, let's try to develop some intuition. Let's throw in some values. So we have 2. So what would be the next term? It will be the previous divided by 2 plus 1 over 2 times the term. So we're going to have 5/4 over here. And then if we plug in 5/4, again, this is not a trivial sequence, right? So we have, what do we have? We have 5/8 plus 2 over 5. So we're going to have 25 plus 16 40ths, right? So we get 41 over 40, and so on. And now if we want to convince ourselves that this sequence converges, we have to answer the following questions. Is this sequence bounded? And is this sequence monotone? So first, let's try to answer the question about, let's try to find its bound, if it's bounded. And to show that it's bounded, we are going to, again, we're going to look at this and we're going to observe some patterns, and we're going to try to speculate, and we're going to say that it is bounded by let's see, it's bounded below by 1 and above by 2. So why would it be bounded above by 2? Because as you can tell, 2 is the largest term, and I guess it does make sense to analyze the monotonicity of this sequence first. So let's answer these questions first. Is this monotone? And to see if it's monotone or not, we have to check whether the successor is always less than or equal to its predecessor. And how do we do that? Well, the n plus 1th term is actually, we have a recursive formula for that, so it relates to the predecessor like this, and we just have to make sure that this inequality always holds. And how do we do that? Well, let's multiply both sides by 2an, so we're going to get an squared plus 1 less than or equal to 2an squared, and we're going to subtract an squared from both sides. And basically it says your successor will be less than the predecessor if the predecessor is greater than 1. And by induction, what do we see here? Well, the first term is greater than 1, so this guarantees that its successor will be less than this term, and then as long as the successor is greater than 1, then its successor will also be greater than 1. And I guess this argument is less formal than we want it to be, but let's see. So since we kind of bouncing back and forward between proving that it's monotone and bounded, this proof shows us that it would be nice to establish the fact that an is greater than 1. And if we can show that, then the monotonicity will follow. So let's go back to proving that this sequence is bounded. And to show that it's bounded below by 1 means we want to show that the n plus 1th term is greater than or equal to 1. So to show that means we want to show this, and we're going to do the same thing here. We're going to multiply the numerator and the denominator by 2an to get rid of some stuff, and now here we're going to subtract 2an from both sides, and this is always true. So an minus 1 squared is always greater than or equal to 0, and since this is always true, that means this will be true. So basically, again, the next term will be greater than 1 as long as the previous term minus 1 squared is greater than 0, but it's always true because something squared is always greater than or equal to 0. So again, this convinces us that an is bounded by 1 below. Now let's go back over here. Now that we know that an is bounded below by 1, that means it's true for all an's, and therefore the consecutive term will be less than the successor will be less than predecessor, which convinces us that this sequence is monotone. Now that we know it's monotone, and not just monotone, we know it's monotonely what? It's decreasing, right? Now that we convinced ourselves that it's decreasing, so we know that this term is greater than this term, and this term is greater than the next term, and this term is greater than the next one. So we see how it is bounded above by 2 because 2 is greater than 5/4, it's greater than 41/40, and so on. So this convinces us that this sequence is bounded. And now the punchline here is that since we just put a new slide, since we convinced ourselves that this sequence defined recursively is bounded and monotone by the 5-word theorem, this sequence converges. Now remember, that theorem tells us that the sequence converges, but it doesn't tell us what it converges to. So to answer that question, what does it converges to, we're actually going to do this little, it's not a trick, but it's a technique. So if the limit does exist, and we just convinced ourselves that it does exist, then it can be found as the limit of the nth term. But if we add 1 to the index here, nothing really is going to change in terms of the limit. So as n goes to infinity, both an plus 1 and nth term, n plus 1 and nth term, they both represent the limit, again, as n goes to infinity. So we can use this idea and we can replace in the general formula the n plus 1th term and nth term with L. And if we do that, we're going to end up with the following equation. So let's subtract 1/2 L from both sides. Let's multiply everything by 2L. And we have two possible solutions. And we have to discard one of them because there's only one limit. And which of these two we are going to discard? Well, remember, the sequence was bounded between 2 and 1. So there is no way it is -1. So we're going to discard this, and the only answer that makes sense is this. So not only we convinced ourselves that this sequence is converging, we also were able to find its limit. So let's do another quick example. Luckily there isn't too many problems like this on the homework, but just for the sake of being complete, I am going to show another example. So let's consider this sequence, and let's verify that it's bounded, and let's verify that it's monotone. And once we verify this, we'll be able to conclude that it's convergent, and then we'll find what it's convergent to. So we can, again, we're gonna have to bounce between those arguments here and there, but first let's convince ourselves that this sequence is increasing. And to show that it's increasing, we have to show that the n+1th term is greater than the nth term. And that means we have to show that this n+1th term is greater than the nth term. And we're going to simplify this, so we have 1/2 an plus 2 is greater than a sub n, and we have 4, or 2 is greater than half of a sub n, and now we have 4 is greater than a sub n. So this will be true if a sub n is bounded by 4. So let's bounce back here and let's try to show that this sequence is bounded by 4. So let's show this, the upper bound is 4. And how do we do that? So to show that the upper bound is 4, we want to show that this is less than or equal to 4. And we want to show that is the case when we plug in, when we replace the n+1th term with this formula. Now let's multiply everything by, let's distribute 1/2. Let's subtract 2 from both sides, and let's multiply everything by 2. So we end up with this. So what does this mean? That means as long as the predecessor is less than or equal to 4, the successor will also be less than or equal to 4. And since the first term is less than or equal to 4, so a1 is less than 4. So this means that a2 will be less than 4. Now it's like an induction, so a3 will be less than 4, and so on. So this is a convincing argument that the sequence is bounded above by 4. Now, is it bounded below? It is bounded below, and it is bounded, we can show that it's bounded below by 0. So how do we show that? That means we want to show that this is the case, and let's see if it's going to be easy. Hopefully it's not going to be confusing. So let's try to do the same argument here. Is it greater than 0? And yeah, let's see. So multiplying by 2, we get the same thing. An is greater than -4. And yeah, it seems like it's gonna work, right? So it says basically, as long as the predecessor is greater than -4, the successor will be positive. Now our first term is definitely greater than -4. So the second term is positive, but being positive means it's also greater than -4. Therefore the third term is positive, and so on. By induction, it seems like we created a convincing argument that all the terms are greater than 0. So the sequence is bounded. Now, because it's bounded by 4 above, now this is true for all successors of the terms that are less than 4. So this altogether now creates a convincing argument that we have a monotone, but not just monotone, we actually show that it's an increasing sequence. So because it's increasing and bounded, we conclude that it is by the 5-word theorem, we conclude that it has a limit. And to find its limit, we're going to use the same technique as earlier. So we're going to just replace every term in the general, not the recursive formula by L. So L is equal to 1/2 L plus 4. Let's solve it. 2L is equal to L plus 4. Subtract L from both sides. L is equal to 4. So we found the limit of the sequence given to us recursively. So it's not always easy, but at least we have now one tool to work with recursively defined sequences.